we're going to take a look at equivalent resistance. Now, you guys just worked through a couple activities that were looking at equivalent resistance, so this should be mostly review, but I want to make sure we're all on the same page. Now, when we're talking about equivalent resistance, we're talking about how we can replace one or two or three or however many resistors we want with one resistor that has the same effect. This helps us in analyzing circuits, but we have to do this differently for resistors in series or resistors in parallel. Now remember, a series circuit has only one path for the current to flow through. So if I put a resistor here and another resistor here, then these are series because the current flows from one through it to the next and then back to the battery. Now because of that, there is actually a relationship here. The current that leaves the battery, I1, or IB I guess, then goes through resistor 1, I1, then goes through resistor 2, I2, then comes back to the battery, those all have to be the same because there's only one place for the current to go. We can't create or destroy charge, so however much charge enters has to leave, however much charge enters has to leave, however much charge leaves comes back. So in a series circuit, what we say is that the current is everywhere the same. Current is everywhere the same. Now, we can write that as an equation as the current leaving the battery is equal to the current through resistor 1 plus the current through resistor 2, and if there were more resistors in series, we could just keep adding those on. But it's also true that energy has to be conserved. So that means the energy being produced by the battery has to equal the energy being used in resistor 1 plus the energy being used in resistor 2. Now usually we think about energy in circuits as power because that's the rate at which the energy is being consumed, and we're going to consume energy at the same rate it's being produced, and so that means the power of the battery, which remember, if you recall, power is voltage times current. So the total voltage of the battery times the total current leaving the battery is equal to the voltage across R1 times the current through R1 plus the voltage across R2 times the current I2. Now, this we can use Ohm's law to help us simplify this a little bit. Remember, voltage equals current times resistance, V equals IR. And we know these currents are everywhere the same. So what I'm going to do is I'm going to go ahead and I'm going to replace, well, I'm going to cross out these currents because they're equivalent, they're all the same thing, and I'm going to replace the voltage with I and R. So resistance total times the current, which is the same everywhere in the circuit, equals resistance R1 times current, and again, same, plus resistance R2 times current, again same, and so again these currents are going to drop out, and what I have is the total resistance is equal to R1 plus R2, and again if this was more circuits in there, we could just keep adding these up to the nth resistor. So that means adding a resistor in here increases the total resistance, decreases the total current through the circuit, and if these were light bulbs, everything would get dimmer. So adding something in series is another bottleneck to the current and prevents as much current from flowing, increases the total resistance. Okay? Now in parallel, this behaves a little bit differently. Okay? And there's a couple reasons for that. So let's draw a parallel circuit. In a parallel circuit, we have multiple paths for the current to flow. So I'm going to put in a resistor here, and then I'm going to grab and I'm going to put in another resistor here. Okay? Now the current can go multiple directions. It can leave the battery and it can go through R1, or it could leave the battery and it could go through R2, and so current can actually split at this junction. Some of it can go this way, some of it can go this way, but the current that leaves here and leaves here, those join back up to come back into the battery. So here the current is not everywhere the same. Instead, what we have is the current leaving the battery is equal to the current through R1 plus the current through R2. Okay, so current is not everywhere the same. But there is something that is the same. If we were going to measure the voltage across this battery, we would hook from the one side of the battery to the other side of the battery. If we were going to measure the voltage across this resistor, we'd hook here and here. Across this resistor, we'd hook here and here. Well, these are all the same spots because this is one conductor. A conductor we consider to have no resistance. Same there, which means voltage is the same everywhere. Voltage is same everywhere. So again, if we look at this in terms of power, the power being produced by the battery, the power of the battery, has to still equal the power being consumed by resistor 1 plus the power being consumed by resistor 2. Energy can't be created or destroyed. Which means we can take this equation and we can say, well, power is voltage times current, so the total voltage of the battery times the current of the battery has to equal the voltage across R1 times current R through resistor 1 plus voltage times current through 2. But since these voltages are everywhere the same, we can cross those out, and I have the current produced by the battery equals, okay, so I'm back to where I started. But I'm going to use Ohm's law, V equals IR, and I'm going to make a substitution. I'm going to solve this for I, so I equals the voltage divided by the resistance, and so now I have the total voltage produced in the circuit divided by R total equals voltage through R1 divided by resistance R1 plus voltage through R2 or across R2 divided by resistance R2. Again, those are all the same. So what I have is 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3, whatever I need, all the way up so I can keep going with this. Now think about what that means. Increasing the resistance by adding a resistor in parallel decreases resistance. It gives another path for circuits or for current to flow through the circuit. So current can go here, or it can go here, or it can go here. Okay, and if I add another one, it can go there, which means there's now 4 places for current to go instead of 3, or 2 places to go instead of 1. So adding a resistor in parallel decreases resistance. Got to be careful with this. When you add up these resistors, you're not finding resistance, you're finding the inverse of resistance. So at the end, be sure you invert that back and get 1 over RT to the negative 1 is actually the total or equivalent resistance of this circuit.